Good morning or otherwise, everybody. It's 2:30 here in Australia. I'd like to introduce myself. My name is Colin Chapman, and I'm a state reviewer for systems engineering in Victoria, Australia. Systems engineering is a subject that we offer at matriculation level in Victoria for students as part of the pathway towards university. And I've also been recently appointed a Academy Fellow for the new Victorian Academy for Teaching and School Education Leadership. I'll be looking at a program that we've had in development now for a decade in system engineering, which has a structure that allows us to reward genuine student engagement with risk-taking in their development of projects. So I'll share that. So in system engineering, the students are expected to build an electromechanical system. It needs to be integrated, relying on some sort of feedback mechanism, even if it's primitive. And we reward risk-taking in this particular subject through a process of intention building in order to be able to genuinely reward risk-taking rather than have risk-taking as a rhetorical exercise from the teacher. There's a genuine opportunity to do so. We make extensive use of Mathematica and systems modeler in this process. It's one of the aspects that's important for us is the idea of modelling and how people's ideas of modelling will change throughout the course of a project as it's being realised. So this is a unique study. We reward the development and modelling of a plan. So a student, typically a class will have 20 students in it. Each student at this level will have their own individual project. They're not assigned, they're not developed by the teacher, they come from the student themselves. And these projects emerge from a need that the student may have identified or some sort of opportunity to develop some product and so on. And the interesting thing about that process is that the teacher has a room of 20 large projects that they can't possibly be an expert in. So it encourages the teacher themselves to be a practitioner, not just a teacher, as they engage with student projects. In fact, it's not unusual for the teacher themselves during the project time to be working on their own project and model the sorts of things that you would do as a project that you've so carefully planned, decides not to go to plan. So it's for the development of a controlled electromechanical response to a problem, situation, opportunity, or a need. And we have a narrative mechanism that allows us to reward risk-taking when the plan doesn't go to plan. And Mathematica and modelling and systems modeler is a large part of that mechanism for developing a narrative approach. So we have three main areas for this particular project. And the first area is that we want intention to be built. So as a student develops a response to this problem, situation, opportunity, or need, we need the student to, at the outset, communicate in some fashion how they understand that. Now, the evidence for showing their understanding at the very outset of the project can take many forms. It doesn't have to be text. It can be interview. It can be audio. It can be a video. It can be a film of the situation itself. It can be a model of the situation they're looking at. So we allow a broad expression of a student's understanding at the very beginning. And this is during intention building. You'll see later on that there's a section where the reward when the student's understanding changes throughout the project of what the actual problem, situation, opportunity, need could be. An example of this might be if the individual is working on some product for somebody with disability, for mobility, for example, or being able to reach objects from a wheelchair, whatever it might be, that their understanding of the problem may evolve throughout the project in multiple ways. So one of those ways might be that the way for the individual to be able to improve their mobility, perhaps that needs to be more autonomous than what they intended in the first place as far as their response was concerned. The student may recognise that when working with somebody to develop a product that is going to be used by them, that perhaps it ought to be co-developed. And so part of the project as a system engineer is to be able to develop some structure where co-development can be used in the development of a product suitable for an individual with disability for the particular need that they may have. They need to be conducting research during this intention building time. And again, their understanding of research can change throughout the whole project. And we reward the students at the end of the project for their reflections and discussion and the narrative process and pace that they go through throughout the whole project, where their understanding of research and how that can be meaningfully different throughout the whole idea. We expect them to work on modelling, simulation, experiments. And in this presentation, we're going to be looking at some of the artefacts they may include in their record of evidence to show that they've done so. And again, we would expect that their understanding of modelling might change throughout the course of the project itself. So an example of that's happened in the last few years in my particular teaching environment, a student developing a wheelchair lift with a short throw that had to be compact, and the student did multiple models. So one of those models was just purely a diagram with physics calculations for vectors and so on to be able to work out the types of linear actuators that they might use for the project and the geometries and so on. They made scale models and they did some other models in software as well. Everything seemed to work. And when they built the product itself was a disaster. It didn't do what it had to do. Well, that student was able to be rewarded from the modelling point of view because they realised that modelling an object isn't just a case of scale with respect to dimensions. You need to model all sorts of things, such as the properties of the material itself and so on. They need to research risk and their changing understanding of risk as the project evolves. And this year was a particularly, and last year, particularly interesting for the students because they can evolve their understanding of risk and realise it's situated. It's not just a static risk analysis that applies for every single workplace. There are circumstances that require you to reevaluate risk regularly, and the students are rewarded for doing that. Then they need to also make a plan for how they're going to learn, how they're going to manage their time, resources. They need to build in agile processes. So this heuristic approach where you build a solution as quickly as possible and iterate. Need to talk about testing and those sorts of evaluations, which would be useful in order to work out how the project is going as it progresses. So we have rubrics that describe these things, and you can see in this particular rubric here, we've got an assessment criteria, and this is part of the intention building. So this is the investigation aspect. And you can see the indicators are shown on the left-hand side. And then we have the levels of performance. So levels of performance extend from left to right, and they go through a increasing significantly more sophisticated application of skill. So we go from, in this case, you can see in the first column, we've got develops a design brief for an integrated controlled system and identifies its context, constraints, and or considerations. So this is just a purely identify, can you list context, constraints, and so on. Then you move to the medium and you can look to the same area in that particular descriptor, and it says outlines its contexts, constraints, and considerations. The next level up, it asks for a description of context, constraints, and considerations. And the final one is explains its context, constraints, and considerations. So you can see the sophistication of understanding progresses from very simple listing type activities, low order verbs, to higher order verbs as you go along. This is evident throughout the whole study. And the reason we do this is because we want every student to have an opportunity to have an entry into this, this activity, this idea. And so we give them a broad range. And those who give a low level of performance for this first part can redeem that in their evaluation at the end when they realise that perhaps their initial engagement needed to be far more sophisticated, that listing constraints is not the same as explaining them. And of course, that would be associated with a justification for someone's response. So now we have the research phase. So devising, designing and modelling design options. So this is where our Mathematica and systems modeler kicks in. And you can see that the descriptor here is talking about modelling of components, subsystems, and or processes. So it's really broad, and you can see why we prefer to use systems modeler for this, because we can do all those things in in the program. Particularly processes themselves, where we're starting to connect discrete aspects of their response together and looking at how they interact, because individual components and subsystems may work fine. It's when they're brought together that can be an issue. They need to identify a number of feasible design options as well. So this is not a one shot as far as the response is concerned. We expect them to develop our magic number is 3, so at least 3 feasible design options, and they need to model all of those design options and then find some fair way to be able to assess the one that may well be the most appropriate. And again, all of that is up for grabs in criteria later on, where they reflect upon what they did and talk about how they worked in a situation where the plan didn't go to plan, because this intention building is talking about how they intended to go about their project. And then the final part of intention building is planning the creation of the system itself. So devising the work plan, referencing material and so on, and their risk assessment. So you can see the descriptors going from left to right, and we've got the key verb here, which at the top end is analysing how materials, components, processes and tools will be used for the creation of the system. And the high level is explaining. The medium level is description only. And the lower levels and very low is simply identifying such things. So you can see again, we've got this increasing sophistication of engagement. And this is a nice thing to have in such a piece of work, because later on they can go and look at what they did in the planning phase and how that could have been different, how they might have been a practitioner differently. So then we have a making narrative. So this is a narrative of the successes that they had, the pragmatics, the ironies, the contingencies. So what did they do? Because they simply had to do it. They're in an agile environment, so they need to get something going, and so they can iterate and also interact with a user if a user is involved in the process. We also have those ironic episodes that happen during system engineering where unintended solutions popped up when things didn't go quite right, and you can grab aspects of that and incorporate that into a better design. And those contingencies that you need to think about. So our solutions are contingent upon the circumstances you find themselves in, and in a schooling environment, at matriculation level, it's contingent upon the access to machines, tools, and other processes as well. So again, we're informed by agile processes and sensibilities. We simply want to get a solution going as quickly as possible and engage with users or engage with evaluative processes and just keep iterating with the idea that we try to build a solution that can be evaluated as being an increasingly better response to a design brief. We're also very keen on an e-record of evidence, and we keep that fairly simple. The students are free to use whatever mechanisms and tools they wish, but we promote the use of Mathematica for this because they can embed video, audio, they can hyperlink from page to page and make a faux website so that when somebody is looking at their record, they can move from particular concerns in the assessment criteria to the evidence directly, and students can link the evidence together. Using Mathematica also is very useful because they can embed simulations, and I can show that as we progress through this presentation. They can put manipulates into objects as well, so they can develop a virtual experiment and put manipulates in it so that the person who's viewing the document can manipulate the simulation and see how the experiment works, not just have a report of how it works. And it allows a more dynamic communication between the student and the person reading the documentation that they produced. So you can see all the sorts of things that can be given as an e-record of evidence, and Mathematica is a tool with the broadest capacity to be able to embed evidence and link evidence together into a narrative that can make sense. We expect them to go through recognition of things that aren't going to plan while they're making. So they've made a wonderful plan in the first three criteria, and we want them to recognise when things haven't gone right. The example this year is that we were in remote learning for almost half the year, and the students had to recognise that that was a constraint or an issue, and then redocument. And part of that redocumentation, or document that problem, and then replan. So part of that replan is that when you move from physical construction to virtual construction of a response to a problem situation, need or opportunity, that other risks come to the fore. Such things as ergonomics of your workspace become quite important if you're stuck in front of a computer all day, and so on. Once you replan, they need to remake, and then they need to recognise the new plan not going to plan. We need this narrative with evidence as they're going along, because the students are able to use that to be able to gain reward for effective risk-taking. So the criteria is here. I won't go into any detail here because I need to move on in order for us to finish this in good time so that we can have some questions at the end as well. But you can see here we've got use of tools, equipment and machines to make the system. And again, we've got a set of elaborations of criteria that go from listing through to justification type activities. And you can see also that implementation of a work plan goes from being supported to being independent. Then we've got realisation of the integrated controlled system. So again, you can see the progression from left to right. And you can see that there's an interest in having documented modifications, and part of that is to recognise when things haven't gone right or how an approach might have to change. And that approach is not just with regard to the materials themselves, but the way that they work as a systems engineer in a particular environment at a particular time on a particular problem with particular clients or opportunities or needs. And then criteria 6 is a diagnostic part of the making narrative. So we've got here the need to be able to, well, going from using diagnostic tests to identifying diagnostic tests, and how they conduct those. And you can see on the indicators, there is a broad range of things that the students need to attend to, including explaining how to set up the diagnostic tests, conducting them, generating and using test data. Now, using Mathematica, of course, we can hook in vernier sensors into Mathematica quite happily and use that to collect data, and that pushes it straight into the Mathematica page. Again, it's a dynamic environment and it's handy for that. They can put tabulation of results and processing of those results and so on, and dealing with data very nicely in Mathematica. So it's a nice, again, a nice environment for the students to pull together a true narrative of the processes they went through, rather than just a pen and paper response to what they did. So the last part here is the plan not going to plan. So we want to reward the students for risk-taking. We have moved well and truly beyond, in this study, beyond saying take risks, you need to be risk takers, to saying, well, no, here's a mechanism for you to be rewarded genuinely for taking risks. So we need discussion of how the plan didn't go to plan. It's key for everybody to understand that the plan won't go to plan. Last year and this year, cases in point, of course, but we can't anticipate everything in general. So we need to acknowledge this as being important to the systems engineering project and to reward appropriately. Given that there are 20 projects going on and the teacher in the environment is working across those 20 individuals, by the way, they're all individual projects, the teacher can't be an expert in all the projects, and they're going to make all sorts of wrong turns and misdiagnoses and so on. But the teacher engaging with the student in this fashion is the genuine teaching moment. It's where the student realises that when their project becomes a train wreck, and the teacher works with them to try things out to get out of that train wreck, that they learn what system engineering can be really about, and why agile processes are really useful for us to develop increasingly better responses to a particular design brief. So it'll include reflections upon planning differently, thinking about agility as a process for an intimate response, and also a critique of modelling and simulation to improve modelling and simulation. So modelling and simulations tend to be idealised at first blush with students. And as the project goes along, they realise that they need to build in imperfections into their model in order for that model to be a more realistic representation of what's actually out there. So we don't have very many inextensible strings and so on. So those sorts of things need to be thought about. Resistors having temperature coefficients and so on is also an issue. So I'll quickly just go over the descriptors there, and my materials are in the files, so you can have a look at this in more detail. So I won't go through it, but again, the whole basis upon this is going from left to right, increasing sophistication from listing, identifying type activities right through to justification activities at the high end. So here's a simulation to communicate concepts. So this is a voltage divider network, and this is a bread and butter circuit for a lot of students because they will have a resistive sensor of some sort that they build from scratch. It could be trying to be a proxy for light detection. or even temperature with a thermistor or an LDR for light, or a pressure sensor, a resistors pressure sensor, all sorts of things. So we like to play with this, and we build a simulation throughout the project, and the students build it. Again, this my workbook is available for you to use and to play with to see how we've done all this. But this is a static model, right? So this is how the students might begin, and it gives out a particular result for a particular voltage. Here is the more generalized one, and a generalized model has got a whole series of manipulates. So you can see the manipulate symbol here in order for them to play with this. And let me go back up again. There we go. So we can go ahead and shift enter all these things. And of course we get the model, and there it is, almost. It's getting there. Give it a moment. I don't know why it hasn't pulled it in. It should be in the file. Okay, they couldn't find the network. It'll be an issue with folders, but those materials are in the files. You'll be able to play with that model itself. In the end, the students will produce a model of a voltage divider network, which has got manipulates for the resistors, and they can investigate how the changing ratio of resistances changes the reading on the voltage divider network. It's a nice little activity. I'll make sure that I put into the files the missing model. It should have been there. I'm pretty sure it is there. Here's a tool to visualize integration, which is quite important. This one is using systems modeler, which I'm pretty keen on, and model plug. And it allows students to have an analog input where they've got particular logic associated with it, and whenever it falls, the signal in blue falls between those two levels, 3 and 4, it gives a digital high that you can see down below. And what I'll do is get out of this one so that I can show you quickly our simulation, which is here. So this is in model plug. I really like this because it allows the students to embed in their electronic record of evidence what's going on from a logic point of view. I find it difficult to do this purely descriptively, so it's nice to have an actual model going on. So I'll just quickly simulate it. I keep my eye on the clock. So you'll notice it'll come up with a whole lot of variables that I will plot because I've plotted this many times before. So I'm going to do the analog output, the digital output, the lower fence and the upper fence. So these are the two values that we're measuring in between. Of course, we go to settings and we synchronize it real time because Mathematica likes to go at 1,000,000 miles an hour. And we will build the simulation up, and as I cover the LDR, you can see the values there. Now, I'll re-simulate that, and I'll just quickly change my camera. If I do that, you'll be able to see the circuit as well. So let me just move a few things around so we can get to that part of the screen. Rid of that now. I was hoping to change the camera, and I'm trying to think of where I want to do that. And I think I might have to stop share for a second, change the camera so that you can see the circuit. So there we go. That's the voltage divider network, and what I focus. And you can see there's the LDR there. There's its 10K voltage, and we've tapped in between there into the analog input of the Arduino, and we've got just an LED as a signal there that goes on and off when it hits particular values. I'll share the screen again and redo the simulation, which means I'll bring that to the front. Do that. So here's a simulation making its way. I'm putting my finger over the LDR, and you can see that as I cover the LDR, I'm getting in orange the digital output when the signal goes between those two fences that I developed in the simulation. So now the students can put this simulation inside their Mathematica notebook, and they can annotate this and show exactly what's going on. So we've got great evidence of integration, so or at least, responding to a signal. So let me stop that share. Now, questions can be put into the chat, which is in the Pathable area, and that's also where I keep all of the other materials. Okay, so I got from Jan a question about imperfections and examples of impressive student projects. So some great projects that we've had over the years, and the imagination has been fantastic. A student developed a pollution monitor with a drone. So the student developed a whole lot of sensors and so on that would be able to measure carbon monoxide, and they would fly the drone over roads at certain times of the day and try to get some sort of map of the carbon monoxide plume over roads, right, compared to an area that's not a road. So that was great. And then they also had landing gear for the drone itself. So as the drone made its way towards the ground again, the landing gear would detect that and then deploy and land. So they had nice mechanical aspect to the project and good use. I've had another project from a student was the development of a water body monitoring system. In fact, I've had a couple of projects like that where they built a vessel, and that vessel is a model boat, and that would then drive out into a body of water, and they were measuring turbidity. So it had a system to be able to lower down a light source into a body of water and a detector at the top to work out how cloudy the water was and so on. And they also made, again, from discrete components, they researched the journals, and they were interested in measuring salt levels. So they did that through a resistive type sensor. And not only did they build that sensor, but as they went through the project, they realized that the sensor was becoming fouled. So they worked on iterations of processes to eliminate the fouling of the sensor itself. So quite neat. We've had students work on other projects such as automatic piano accordions, because that was their obsession, that would be able to read music and play it and so on. We've had other responses for pull-along water purifiers. So a student recognised the need in some communities for people to go a long way to collect water. And so they developed a system where the vessel for collecting the water was on wheels, and as the cart was taken back to the place of living, the water would be filtered through a number of processes. So a range of projects that are meaningful, and I emphasise this is a matriculation level, And the way we've designed the project, it allows students from a broad range of backgrounds to perform at practically university level, whilst being in the last years of their formal schooling. And Jan has also asked, how the requirements and use of Mathematica and systems model be influenced by the lockdown? Well, we've had 2 years of lockdown, and it's been a lifesaver with respect to student engagement and keeping them in the game. One of the things that's really great about system engineering is that the students build artifacts, and those artifacts are a focus for their ability to communicate about what they achieved. It's something we need to build into other learning areas in education. And those artifacts are both physical artifacts as well as virtual ones. And having virtual artifacts through Mathematica and Systems Modeler have been a real boon, because we're able to keep encouraging the students to be fully engaged with their projects, and to be able to communicate as well. Its narrative approaches to assessment really does thicken our description of learner achievement, and that's why we like to use these particular products. Thanks for that link there, Jan. I'll have a look at that. But yeah, it looks interesting. I'll click into that afterwards. All right, I'll give it a couple more moments if anybody wants to type in a question. I'm more than happy to talk with people as well. I think there's an ability to contact me through this process if you're interested in having a discussion about implementation of these sorts of programs in your own environments. I'll give a couple more minutes for any questions. All right, I'll just change the camera back to my pretty face. That means I'll need to go to stop share, I think, again. Yeah. There you go, that's me. And I'll just double check there's a chat here. All right, yep, somebody just told me to change the camera back, and I did. Good. All right, so let me close that. And I'll just go back and just check if there are any additional questions. All right, so again, I'm open to discussions with anybody at any time. More than happy to talk about this. One of the things I'll be doing in my new role is extending these narrative processes using such things as Mathematica and Systems Modeler into mathematics as well as sciences. And I'll be doing that on a statewide basis. We have also more recently written in simulation, modelling and computation in the new Australian curriculum. I was involved in that process for mathematics. So we've enriched the Australian curriculum for mathematics by using these sorts of processes right from K, so the very early years of schooling, right through to matriculation level. So we're giving students an opportunity to be more richly engaged with the learning rather than just going through a process of repetitive calculation and so on. We and I have been greatly informed by the text Maths Fix by Conrad Wolfram. It's been a boon for us in learning improvement, and as I say, we're trying to extend that in Victoria, in any case, across all the learning areas, a process where we can reward genuine risk-taking. So I thank you for your attention to the presentation, and I hope to hear from people at some time in the future. Thanks.